Okay, now is the time. Let's welcome Ting himself from Google and AKA the Ting of many things to bring us the fully open source manufacturable PDK for 130 nanometer process with fully open source tooling and no cost MPW Shuttle program. Okay, hand over to you, Tim.
Cool. Hi, can you hear me okay? Are we all good?
Yeah, we can hear you perfectly fine.
Cool. So I want to first say, hi, I'm Tim. I'm a software engineer. I've been doing open source since the mid 1990s. And I've been working at Google for about 12 years now. And I do want to mention that, Google is a large place. I think we're like 150,000 people. And so we're doing lots of different things. And this is mainly what my group at Google is concentrating on. So one thing I've learned in the 12 years I've been here at Google is that Google runs on computers. It runs on a lot of computers. And for a long time there, we had this great thing called Moore's Law, where you wait a year and all of a sudden everything is faster and easier. However, recently, Moore's Law is no longer keeping up. And the thing that makes this problematic for someone like Google is that all our demands are still continuing to grow. This is looking at YouTube hours per minute uploaded. And so with the end of Moore's Law, we're increasingly having to look towards things like hardware accelerators. Google developed the TPU because the TPU was needed to keep up with machine learning workloads. I think there's a story that's told that if we hadn't invented the TPU, we would have needed more compute than is available in the world by 2025. But what we've discovered when developing these hardware accelerators is that developing hardware accelerators is very expensive, and it's getting more and more expensive. We're also seeing that the actual benefit we're getting from shrinking down the transistor is not as strongly beneficial as it used to be. There's this gap between what theoretically we should be getting and what we're actually getting. And as I mentioned, I've been doing open source for a long time, and open source has really enabled the software developer to be a lot more productive. And it's really important to making Google possible is fully open source software like GCC, like Linux. And so I started to look into how do we apply open source to silicon, and particularly hardware accelerator ICs. And so what do you need to create a ASIC? Well, I kind of divide it into three parts. And the question was, is there open source in these three parts? And so first we looked at IP libraries, RTL, and there's actually a long history of openness in RTL. In fact, I believe Stafford Horn is giving a talk about OpenRISC, which has been around for almost, I think, 15 years now. And so there's a library of IP out there that's fully open source. And if you look at the massive explosion of RISC-V IP, there's definitely even more coming. It turns out there's also been open source EDA tools for a long time. If you go and look at Tim Edwards' open circuit design, there's also the Alliance and Coriolis flow from the French university. And DARPA has recently funded this IDEA program, which has developed OpenRoad. So there are EDA tools that enable you to create open source ASICs. And then I discovered that you need a PDK as well. So what is in a PDK? Well, a PDK contains all the design rules you need to comply with to make your ASIC actually compatible with manufacturing. It also includes all the information of how, when your device is manufactured, it will actually perform. And I thought, this is a very low-level thing. It's kind of like a libc or, a low-level specification that I have in software. And so I went looking for open source PDKs, and I couldn't find one. There was a lot of stuff out there, but most of it was either non-manufacturable or under not open source licenses. And when I started, ASAP 7 wasn't open source. It's now open source, but it still remains non-manufacturable. And the reason this is super important is if you take something like what efabless did, they were trying to develop a fully open source chip. They had a fully open source RTL for the design. They had a fully open source tools to build the design. But because they used the XFAB 180 nanometer PDK, which was a closed source PDK, the PDK infected the rest of the design, meaning that they weren't able to release the full design for anybody to replicate. And this kind of set off this idea that to make fully open source ASICs, you need a fully open source PDK. And I investigated this space a lot more and actually ended up writing a paper for ICCAD 20 about what I identified as the missing pieces needed to make fully open source ASICs. And I identified 4 major roadblocks. And this first was the lack of open source manufacturable PDK. Luckily, I work for Google, and Google has the resources to actually solve this problem. And so in partnership with the Skywater Technology Foundry, Google released a fully open source 130 nanometer manufacturable PDK at this URL. It's under an Apache 2 license, and it's hosted on GitHub. Just like any software, there's no NDA to sign. You just go and clone the repo. And so what is in this PDK? Well, it's a 130 nanometer node. It supports internal 1.8 volts voltage with 5 volt I/O. It has 6 layers of metal, one which is a local interconnect, and a lot of optional components like Sonos shrunken cells, MIM caps, high sheet road poly resistors, high voltage extended drain, NMOS and PMOS. To me, that doesn't mean a lot. I come from a software background, but if you're a ASIC person, this hopefully is making you reasonably excited. The thing is that most of this data was documented in PDFs and stuff that, as a software engineer, I don't like using. So when in the process of open sourcing it, we released all this data on Read the Docs, just like software projects are released. And so you can see here is an example of the documentation. And here you can see some of the design rules that actually are specified in the documentation. And you can search this with, a little search engine you might know of called Google. And this makes it so much easier to find what you're actually looking for. And this is kind of what the stack up looks like for Skywater. And what we currently have available is digital standard cells, I/O libraries, base primitives and DRC, analog SPICE models. We have SRAM macros released. The build space is almost there. It should be released anytime soon. And we will soon have some new technologies being released, including ReRAM and advanced high-speed I/O. And when I say digital standard libraries, these are actually quite a comprehensive library of multiple different styles of standard cell libraries. And as you can see, these libraries have a large number of cells in them and a variety of different types of cells. We're also automatically generating symbols and schematics. This is a scan chain flip-flop, and you can just look at the GDS. And to prove that this PDK has everything you need in it to do your own thing, we worked with James Stein at the Oklahoma State University to design a completely new set of standard cells on this PDK. This PDK, as I said, includes SRAM and optimized SRAM cells. And so you can see these here. Normally, like to see these, you would need to sign multiple levels of NDAs. And the thing with SRAM cells is, though, you need more than just a cell to produce a memory. And so we worked with OpenRAM to create a memory compiler that's able to use these SRAM cells that is completely open source. And Matt Goodhouse, who leads the OpenRAM project, actually gave a talk last year on the Sky 130 support. And you can go and look at the YouTube recording there. In fact, in partnership with the Free and Open Source Silicon Foundation, we did a complete talk series about the various different parts of this space. And so with an open source PDK and open source PDK data, you can create a fully open source ASIC. And this is really cool, but it required a lot of work from a lot of different people. efabless was a key partner, and I believe there are some talks later from people involved in efabless. We also had a lot of academic partners, as I mentioned. And the response was somewhat amazing. If you look at this graph, in the first week, the Skywater PDK achieved the same amount of stars as projects like Hyosis and Chisel, which have been in the open source space for, 5 to 10 years. And I think this really shows how much of a demand there was for this PDK. As well, we have an open Slack channel that anybody can join, including people here. And this Slack channel now has 1,800 members in it. And so that was the PDK, and there's a community growing around it. But like growing the ecosystem, the difference between hardware and software is really you need to do manufacturing to find out whether your results are real. And so Google partnered with efabless to create an open source shuttle program, and we wanted to lower the barrier to entry, so we made it a no-cost shuttle program. Google's footing the bill for all the manufacturing here, and efabless is managing the program under our guidance. And the thing we wanted to do was to change the way shuttle programs are perceived. We wanted to make it so that when you're doing these open source silicon, is that your prototypes should be throwaway. They should not be uniquely precious. It's very common for people to do a prototype and then take one chip and mount it in some special area, and then you don't let the intern near it or anybody look at it funny because it's going to waste 2 years worth of research. What we want to do is see these prototypes be shareable. We want to see you have lots of them. And so the way the program is working is that anybody can submit. Your design has to be fully open source. And when I say fully open source, yes, I mean down to the GDS. There's 40 slots. You submit them to efabless, and it's put in a standard harness, which has a RISC-V processor, some power regulation, and some memory. You get 10 millimeters squared, and you get back around 100 ICs that are fully packaged, ready to go. We're even planning for some of the runs to get you back ICs already mounted on PCBs, so you don't even have to worry about that. The standardized harness is really what allows us to provide you with packaged ICs that are ready to go and give you a lot of internal debuggability about what your ASIC is doing. And this harness is mainly being developed by efabless, and it's called Caravelle. Caravelle looks like this, and you can see a couple of designs on the side there embedded in the Caravelle harness. And we're definitely hoping that the harness continues evolving. My eventual goal is to get us to a stage where something like the Caravelle harness has things like USB 3 already enabled in it, so you can have things like high-speed internal logic analyzers and high-speed analog to digital converters, so you can analyze your internal circuit and your internal ASIC without having to have lots of expensive equipment. And the idea is, you get your chip back and you can just plug it into your laptop and go. And so to make all that possible, Caravelle is a really important part of that, and would love to see people helping evolve Caravelle to enable more of these features. And as part of this program, we wanted to make sure there were plenty of opportunities to do tapeouts, and there was plenty of opportunities to improve on your design. The first time you do something, it's obviously not going to be really good. So what we want is people to do something and then improve it. And so we had multiple times that we are planning to run this shuttle. And if you look at these dates, you might notice that November 2020 was, last year. It's currently past. And the interesting thing about this is that we got 45 designs in 30 days from 76 designers for Caravelle. And we only gave them 30 days notice between the time we opened accepting the projects to the time we closed. And a really, really cool thing, and this is something that's super exciting to me, is 60% of these designers had never done an ASIC before. These were people who their first design was enabled by this MPW program and the open source PDK. And the MPW one had such a wide variety of different designs. It had open processor cores, it had full socks, even had a cryptocurrency miner, it had an amateur satellite radio transceiver, a whole bunch of analog and RF, and even 6 eFPGAs. If you're also paying close attention, you may have noticed that MPW2 also was recently finished, and we got another 40 designs taped out and ready to go. And in MPW2, 1/3 of the developers submitting a design self-identified as not hardware people, but software devs. And we've even seen some really cool things where Matt Venn took 16 designs from a whole bunch of people who were taking his course and combined them into one slot, because it turns out 10mm squared at 130 nanometers actually is quite a lot of space. And so I think this opens up a lot of opportunities for people to do their own, multi-project wafer inside a multi-project wafer program. And Matt Venn released all his tools as open source, so you can go and do exactly what Matt Venn did. And this is also why we wanted to get back people so many ICs, because if you've got 16 designs and you're only getting back 6 ICs, who do you give each IC to which people? And so by giving you back a couple of hundred ICs, we really enable things like this to occur. And while the Google program requires your designs to be fully open source, our partners at efabless also released a commercial program, which I think is some of the cheapest way to do ASIC design so far. For under $10,000, you can get your own slot where your design doesn't need to be open source, or you can purchase 1,000 parts at $20 each. And that really enables you to do low volume manufacturing and really prove that your idea is worth doing without needing to raise, millions of dollars of capital. And so I'm really excited about this Chip Ignite program from efabless to enable even more people to open and enter this ecosystem. And so if you look at it, there's still actually 2 more tape-out chances this year. Before the end of the year, there'll be MPW3 and MPW4. There'll be at least 1 more chip ignite shuttle, and there'll probably be even more. And so in 2021, we're going to be doing more than 200 designs taped out. And in 2022, maybe it's going to be thousands of designs taped out. And so you might be looking at this and thinking, damn, I'm too late. But it's not too late. There's going to be more tape outs. There's going to be 2 more this year, and there's going to be more in 2022. So there's plenty of time for you to participate. And the great thing is that there is 1,800 members in the Skywater Slack channel who are able to help you and now have experience doing tape outs with this process. And so now there's no time like the present to become involved in doing open source ASICs. And to give you a little tidbit about what I'm planning in the future is, as I said, we're looking at adding cool technologies like ReRAM to the Sky 130 program. We really want to get people these new technologies that are yet to have a lot of use so people can explore. We're looking at adding programs around an advanced 90 nanometer node. We're looking at adding an even cheaper option for 180 nanometers and a second foundry providing an alternative 130 nanometer process. And all of these we hope to have, both open source and commercial programs to enable people to tape out quickly and easily on these programs. And I really think that the open source PDKs enable the IP and tooling open source ecosystems to flourish in a way that they've never before. And so I'm super excited to see what's happening in both those areas. This is a map that I attempted to draw of the whole ecosystem. And these are the areas that my group is really focused on. As I mentioned, we're really focused on ASICs that are in the hardware accelerator space, and we really want to enable new developers who previously wouldn't do hardware design. And so we're looking very strongly at things like automated tools. And while developing this map, I actually discovered that there's another way to look at this ecosystem. I've been talking about this ecosystem in terms of tooling, IP, and PDK, but you can also think about it in the terms of what is each part used for. There is interfacing with the external world, there's doing some computation, and doing storage. And when you start to think about things in this way, you actually get a picture that looks somewhat like this. And you can start to see how the various bits that I've been talking about start to fit together to build a complete ecosystem that enables people to do significantly more advanced stuff. But as I said earlier, there are actually 4 major roadblocks that my paper in ICCAD 20 identified. If you go and read that paper, you can understand all 4 roadblocks. But if you look at the other 3 roadblocks, this is what I came up with. And so manufacturable PDK, that is well under control and continues to be successful, but there are still other areas that need work. And so my team has also been working with these areas to improve the state in that area. Since I'm only limited time, I'm going to skip through them pretty quickly. But the first one is this place and route tooling. When I gave the paper, place and route tooling was still in its infancy in the open source world. Luckily, we weren't the only people to notice this. The DARPA group in the US government had also noticed this and launched a program called IDEA, which as part of that developed this thing called the Open Road Project, which we're now using very heavily. And like us, they're heavily focused on how do you remove humans from the ASIC design process. At the moment, humans are heavily involved in fixing the output of these EDA tools, whereas the Open Road Project is aiming to take RTL and produce, manufacturable results without a human needing to fix up anything in the process. And they want to do it within 24 hours. And so this is a really awesome project that is really helping drive forward the place and route tooling and really enabling new people to get involved. And I think that's really, really important, is that there are plenty of people who the current tooling doesn't really help get stuff done. There's plenty of people who can get stuff done, but there's even a bigger group that can't. And this is really enabling that group. As well, the next roadblock that we identified is that there is a large amount of system Verilog IP out there that is currently not usable in the open source land. And Google is a big system Verilog shop internally. So we set out to improve the state of system Verilog support in the open source world. And we actually ended up taking a two-prong approach to this. It turns out that if you want developer tools, you actually need a different style of tool than if you want, a synthesis or simulation engine. So for system Verilog developer tooling, we released a project called Variable, and I actually haven't updated the link here, but it's been transferred from Google to the CHIPS Alliance. And it has, a linter, it has a code formatter, think like Clang format, and it also has tooling for doing things like indexing and cross-referencing your system Verilog code. And the key thing is this is able to handle unprocessed code. So you can do things like reformat your code in the same way something like Clang format would without having to expand all the macros. And so Variable is really cool. It's also super fast. When you're, reformatting all code at Google, you need something that's really fast. But Variable wasn't suitable for simulation and synthesis. So we worked to develop this other parser called Shorlog that's Antler-based, and a interface called UHDM, which allows the parser to be separate from the simulation and synthesis tool. So we're using the same parser to connect to Verilator, a very popular simulator, and Yosis, a very popular synthesis tool. And the idea here is that it allows us to potentially change the parser front end without having to go back to the scratch. It also enables people to write new simulators and new, synthesis tools without having to start from scratch with system Verilog parsing. And so this is a really cool project that I hope enables an explosion of new attempts at creating simulators. Verilator is very good, but I think there is a real opportunity around things like distributed simulators. But who wants to write a simulator when their first step is how do you write a system Verilog parser? Other things that we identified was that we really needed a fully open source memory compiler. And so we're working with OpenRAM to create that. And that's been very successful. We also figured out that we need some way to solve the analog problem in a fully automated manner. And so we don't actually know how to automate analog yet. And so there's a couple of different approaches we're looking at. One is working with Berkeley and the Berkeley Analog Generator, or BAG. We're also working with the University of Michigan around this tool called FASOC. It uses a different way of doing things, that makes analog potentially auto-generated. And FASOC is really exciting because there's a fully open source version now. So just going back, if you want to get more details about all these things and dig into them deeper, go and see my ICCAD 20 paper and you can understand 4 roadblocks. But the key thing is that growing the complete ecosystem is something that is a bigger task than just Google can do. So we're working heavily with a lot of different partners to make this possible. For developing the tools, we're working with a wide variety of both big and small partners, people like IBM, Intel, Antmicro, efabless, Western Digital, are all contributing to various bits of this open source ecosystem. There are also multiple different organizations that we're working with and are focused on many different areas. The CHIPS Alliance is definitely a really important organization that I'm working very heavily with. But you can see other things like the RISC-V Foundation, the Open Power Foundation, the Open Compute Project, Open Titan, Low Risk, the FOSSI Foundation, the Open Source Hardware Association, all these groups have some part to play in making these fully open source hardware a reality. As well, I'm working with a huge number of academic partners, and that list continues to grow. So if you're doing something in this space or you want to do something, you can help. You can be part of this open ASIC revolution, and you may even tape out chips as part of this. And I want to come back to the MPW1. 60% of people who were doing a tape out on MPW1 had never done a design before. And I think that shows that you can really participate even if you've never done anything in this space. And if you're looking to partner with my team at Google, my suggestion is to really focus on the open source tools and the open source PDKs. I know that there are some people out there who are like, well, 130 nanometers is a 20-year-old technology. And you're right, it is. But it's also a much cheaper technology than something like 7 nanometers, so it's much easier to experiment with. And these open source tools and open source PDKs allow you to share your work. And so I think the biggest thing actually is create an open source community, which is what I really love about this conference that you've got going here, is you've got a community of people coming together to look at this type of thing. And so that's why I'm excited to talk here. And that's why I'm looking to do more things, especially with groups in Taiwan. I like to consider myself a global citizen. At the moment, a lot of my stuff is focused in the US, but that's just because I have connections with people in the US at the moment. I would love to have more connections with people in Asia. I'm originally from Australia, as you may tell from my kind of funny accent. And I'd love to have more connections with people in Oceania as well, and people in Latin America, and people in India, and people in Japan, and people in Europe. There's so much work here to do and to really create a really thriving open source community that we have plenty of work for anyone in this space. So I recommend you come and join these two things like the mailing list, and as well, really come and join the Slack space. There's lots of interesting discussions going on there, half of which I don't understand, around things like analog design and, developing courses using open source tools is a very hot topic. RISC-V is obviously a very hot topic. So thank you for having me. And I really do want to say that there's opportunities here for everyone to be involved.
Thank you, Tim. And we have, a bunch of questions on Slido. I will bring up the screen and maybe you can answer it. So the first one in my experience, different manufacturer will have different design rule. How Sky 130 deal with the DRC and to match different manufacturer, can we use select manufacturer?
So the Skywater PDK is for the Skywater's Foundry 130 nanometer process technology. So that PDK is specific to that process node. I do want to also mention that, these other PDKs we hope to release in the future are going to be different, and they are going to have different types of rules. And so we don't deal with that. We just, provide the data which enables people to build tools on these different platforms and work with these different platforms. Things like Open Road actually enable people to create RTL that is compatible across multiple different PDKs. The problem is that they don't have many open source PDKs that they can use in their test suites, which makes it hard to verify this is all working. This is why getting more open source PDKs out there is a high priority for my team. And so that's kind of, focus is to enable and supercharge these tools to work with multiple different PDKs, because there are multiple different PDKs available. It's very hard to do this when you only have access to one PDK. You're totally right. And we're hoping the future helps solve this. So the next question seems to be, how do you provide incentives so that designers actually test their designs? Well, most designers want their designs to work. Throwing designs in and not testing it is a great way to get back paperweights. And the other thing is, because we're getting back a lot of chips, there's an incentive for people to share their chips with others so that there's more verification done. If you only get back 5 chips, there's a likelihood that only 5 people are ever going to test your chip, right? Whereas if you get back hundreds of chips and somebody like Ruanlan is like, I would love to play with your chip, I can go, sure, I've got some sitting on my desk, I'll put them in the mail and send it to you. And because I have so many, it also doesn't matter that a bunch get lost in the mail when I send it to him, So we're trying to change the incentives around verification to be highly focused on building stuff that other people use and reuse, and enabling lots of people to cross-check their results. One of the things I find super frustrating about academic papers in this space is that, nobody's able to reproduce them. Nobody is able to take exactly what they did and tape it out and get exactly the same result. And so we're hoping to change that by enabling these open PDKs. You should be able to tape out exactly what somebody else taped out and verify you get the same results they did. And this is going to totally change how people do test and verification, because at the moment it's very focused on, correctness. But, if something is correct but still does the wrong thing as the user defines it, not as the spec designer defines it, it's not a good experience. So we're very much trying to enable a much faster iterative approach.
Okay.
Hopefully that answered your question.
Yeah. We have a question just bump up to the top because he got 3 votes, and his question is, or her question, you can see it right. Okay, just
so the question is, 60% of the designs were done by first-time designers. Do you know how many of the resulting chips worked? I do not at the moment. They should be back from manufacturing anytime real soon now. The interesting thing is that, all results were DRC clean, because the Open Road tools only are supposed to produce DRC clean results. This kind of lowers the barrier to entry quite a lot. As well, by having that harness, we can build things like the ability to turn on and off the I/O without, the rest of the system necessarily working. And, there's this kind of idea that, if you turn on a part of the chip and the chip stops working and starts smoking, maybe you shouldn't turn on that part of the chip again. But by having, this type of control and this internal debuggability, it allows people to try more things and, experiment more freely. And that's what we're trying to do. And, ultimately, these chips are quite cheap. So it's not like you're spending $1 million and when it doesn't work, you've lost $1 million. So we're less worried about this problem. Cool.
Okay, so we're actually 10 minutes over the times, but I guess we can have just maybe 1 or 2 questions, or our editing group is actually ramming at me, so I'm just let us just get this question answered and we can call it off now. Okay. So suppose it's under NDA to disclose it. Yeah.
Well, the manufacturer is Skywater Technology. There's no NDA here for this. You can go and look at who's doing the manufacturing because the design rules only work with one foundry. There's no secrets. And Skywater only have one manufacturing plant for ASICs. So you can go and look up where their foundry is, and you can actually even know where in the world it's being made. Okay. I saw there's are there open source designs available using the open source PDK? Yes, there's 40 of them from MPW1 and 40 of them from MPW2 that are all linked from the efabless website that you can go and look at. They vary in quality, size, how many people developed it.
Okay, and I guess this is the last 2. Maybe we can make it quick.
I do agree that there is still a large gap between open source tools and commercial tools, but the gap is closing quickly. And if you look at things like OpenRoad is being tested at things like 7 nanometers. And so there's definitely work to do stuff at 7 nanometers. And, it is able to produce designs there. I definitely say microcontroller chips are well within the capabilities of the open source tools. Once you start getting to something like an Intel design, you're probably not going to do it with open source tools yet. But I see that changing in the future. And the last one seems to be a custom ASIC will be sold in a vendor machine. I assume that's like a vending machine. Sadly, the physics behind ASICs at the moment mean it takes about 6 months to actually physically manufacture, not 6 months, 6 weeks to manufacture an ASIC. So you're probably going to be waiting a long time at the vending machine if it's creating a custom ASIC. But I'm hoping that, people are going to make commercially viable ASICs on this process node. There's a lot of interesting things you can do now that are extremely cheap to do. So definitely you should go and, create chips. And the thing is, your design needs to be open source, but open source doesn't mean that you can't, make a company around it. Like Red Hat is based entirely around, open source software, and yet they were one of the biggest acquisitions by IBM recently. There is lots of money to be made here as well. It's not just, Google's investing in this, not because it is philanthropic. We're investing in this because we think it makes real commercial sense to change the way ASICs are done and to drive new innovation in this space. So, yeah, maybe if somebody can figure out a way to make it profitable, you could have a vending machine that has custom ASICs being produced from it.
Okay, that will be all. And thank you very much, Ting. And by the way, I just posted the official announcement of our panel that will be held later. And if you have time, maybe feel free to join us, and Dr. Arvis, Dr. Lee, and I believe that there will people from efabless will join us on the panel. Maybe we can discuss more on this because we're overly over time now. So I'm gonna pull everything off right now from the StreamYard. And thank you very much. Bye-bye.
Thank you for having me. It was great.